Okay, now that you've gotten some facts on NASA and NASA Langley, let's see what type of extreme tests NASA Langley conducts at the Aircraft Landing Dynamics Facility.
The what?
The Aircraft Landing Dynamics Facility. But that's a mouthful, so they call it ALDF, or ALDF for short. Let's find out how NASA engineers are using math, science, and technology to solve the problems they're faced with every day.
How is the test set up to solve the problem?
How are graphs used to find possible solutions?
What visual method did NASA engineers use to represent their solution?
The ALDF allows NASA Langley to test tires, wheels, and brakes of vehicles like airplanes, cars, trucks, even the Space Shuttle orbiter, and makes them safer for everyone. For example, because jet airplanes and the Space Shuttle land at really high speeds, we have to simulate those speeds here at the ALDF if we want our test to be accurate. This is done with the use of pressurized water, a carriage, and the tire or gear being tested. 10,000 gallons of water push the carriage down a track. When the desired speed is reached, the tire is lowered onto the test surface. Instruments are used to measure the forces acting between the tires and the test surface. These data are collected by a computer and made into a graph. By comparing many graphs, we are able to predict how a tire might behave under conditions other than what we test. Some of the many tests we've conducted at the ALDF include something known as hydroplaning. That's when you drive your car or land an airplane too fast on a water-covered road or runway, and you actually start skiing on the water. That's fun if you're boating, but not very fun if you're in an airplane. So the engineers at the ALDF figured out that putting grooves in the runway gives the water a way to get out of the tire footprint to keep you from hydroplaning. This idea found its way to the highways you and your family drive on to keep you safe in the rain.
Wow, so NASA Langley engineers have solved lots of real-world problems.
That's right, but remember the ALDF only simulates tire wear, landing speed, and runway surfaces. Sometimes in order to solve real-world problems, you have to go to where the problem really exists. Take Kennedy Space Center in Florida, for example. This is the #1 landing site for space shuttle launches and landings, and the conditions have to be just right for the space shuttle orbiter to take off or land.
Conditions? Like the weather?
Well, that's part of it. If conditions like the runway texture and the winds aren't just right, the space shuttle tires will wear out and could fail. You see, the runway at Kennedy Space Center was built very, very rough, so the water would drain off of it, and it wouldn't be too slippery when it was wet. We didn't want the orbiter to hydroplane. But because the orbiter tires land with the weight of about 150 cars and as fast as 250 miles per hour, the rough runway was like a cheese grater on the tires. Too much wear could cause the tires to fail during a landing, and we want to prevent that. Tire wear gets even worse when the orbiter lands in a crosswind.
Yeah, I've heard that term before. But what exactly is a crosswind?
Well, a crosswind is the wind blowing at an angle across the path of an aircraft. Landing in a crosswind actually causes all of your tires to roll slightly sideways. We call that a yaw angle. And just a small amount of yaw angle can cause a tremendous amount of tire wear. This tire wear limits the amount of crosswind the shuttle can land or launch in, which causes delays. NASA wanted to double the crosswind limit that the shuttle could launch or land in safely. Our job was to find out how to smooth the rough runway surface to reduce tire wear without making it too slippery when it was wet.
So Bob, I guess you used the ALDF to figure out which runway surface to use at Kennedy.
That's right, we started right here. But because the test track here at the ALDF is only a half-mile long and the runway at Kennedy is 3 miles long, we really couldn't take a bunch of short-distance runs here and add them together and accurately predict the wear for a whole shuttle landing. We needed a full-scale test. Somehow, we had to make the shuttle tire think it was on the real shuttle.
Well, how did you do that then, without using the real shuttle?
Well, some very smart people at NASA Dryden Flight Research Facility in Edwards, California, came up with the Convair 990 program. This took the idea of the ALDF one big step forward and allowed us to land an orbiter tire on whatever runway we want, all at full scale. A large fixture was built in the belly of the airplane that could apply the correct weight to a shuttle tire while the pilots landed the airplane at about 250 miles per hour.
Okay, so the Convair 990 could simulate a shuttle tire landing pretty well, but how did you figure out the best runway surface?
Well, that's a good question. Before we put the Convair 990 to the test, we had to get an idea of what kind of runway texture might or might not reduce tire wear. Building lots of 3-mile-long test strips would be very expensive, so we conducted a sub or small-scale test using a test vehicle from Langley. This truck allowed us to wear out smaller airplane tires by rolling and yawing them on lots of different textures. And it allowed us to predict which surfaces might be worthwhile to install in 3-mile-long test strips.
How do you measure tire wear?
Well, after rolling these smaller tires a certain distance, we would weigh them and see how much rubber was worn off. Then we graphed that lost weight with distance. This graph shows tire wear for some of the different surfaces we tested. We tested 18 different textures in all. On the graph, we put a line showing the maximum amount of wear that we could live with to reach our new crosswind limit. Any surface that showed wear higher than that limit would be out of the question, and you can see that limits our choices.
Cool. So now you had 5 runway surfaces instead of 18. What's next?
Next, we conducted friction tests on the surfaces when they were wet to see how slippery they might get in the rain. This graph shows the results of those tests. We also put a line on this graph showing the minimum friction level that we could live with. A surface with less friction would make it too hard to steer or stop the shuttle if the surface were wet. This also limits our choices, and when we combine these two graphs, it said that we could only predict that 3 of the original 18 surface ideas would both reduce wear but not be too slippery. With our top 3 choices, we built 3 test strips and landed the Convair 990 on each of them. Comparing graphs and making predictions really helped us to narrow down our selection of expensive test strips.
Okay, so how did you collect data from the Convair 990?
Well, during our tests, we measured the tire forces with sensitive instruments, and then we used a computer to graph the results. We also combined video footage of each test to find out when each of the tire's cord layers were worn through by counting them. Finally, we could graph the forces and the tire wear and compare the performance of the new surface with the rough surface. This graph showed that we got less tire wear for the same forces on the new surface, just like we predicted. Using all these test results, NASA shuttle managers now had the information they needed to decide to change the texture of the entire runway surface at Kennedy Space Center. That's almost the equivalent of 100 football fields. Today, the shuttle orbiter has the ability to withstand twice the amount of crosswind without worrying about tire wear, and we use measurement, graphs, and predictions to do it.